It's my great pleasure and privilege to introduce our speaker this morning, Peter Ungaro. Peter is the CEO of Cray. He is also a great friend and a great supporter of the Blue Waters Project and high performance computing. And he's going to share with us views of whatever he thinks are relevant for us. So we didn't pre-negotiate what he's going to talk about, but I think whatever it is going to be greatly interesting. I appreciate Pete coming down here specifically for this, and he has to go back to his next adventure. So it's hard to get Pete to be in one place at one time. But I really appreciate his time coming down here, and he's dressed down more than I've ever seen him before. So,
thanks, Phil. Yeah, appreciate it. I figure I get to come out here to a little resort. I can, this is what I look like in the office. Normally, if you snuck into Seattle and saw me, this is what you would see. So I want to take a few minutes and talk a little bit about kind of where we've been, where we're going. Overall, Blue Waters is a very special program to me personally. It's one of the biggest programs we've ever done as a company, and we've learned a lot from it. Every time we build a very large supercomputer, we learn about things that we should be doing better, and I think that continual learning is what continues to make our company stronger and stronger. Over the years. So I'm going to take you through a little bit of what's going on, how we kind of see things in the industry, what we're reacting to at Cray, and hopefully at the end we'll have a little bit of time and talk about the presentation overall or any other questions you guys may have. So I'm going to kind of highlight this discussion around a lot of things are changing in the world of supercomputing today. And when we look out over the next few years, we're going through some of the biggest set of changes in our industry that we've seen in a very, very long time. But while a lot of things change, there's still a lot of things that are going to remain the same overall for us. Three things for Cray, I would say, that haven't changed. Number one, absolutely our commitment to innovation. One of the things I'm most proud of, I've been now at Cray over 12 years, and one of the things I'm most proud of is every year we've increased our R&D investment. We continue to grow R&D, and with all the new technology that's going on in the world, you have to do that to stay ahead over time. Another thing that we've done, I think, really well is every supercomputer that we've ever designed, every one, has been in partnership with one or two or a very small number of customers that we worked with very, very closely and really kind of worked through that. And the second is a real focus around supporting our customers. With big supercomputers, not everything goes well. These are really, really difficult machines to manage, to take care of, to keep very operational and have high effectiveness and efficiency of the resource. While we always wish that our supercomputers do better, one thing is that we will stand with the customers, our customers, in helping them to make those machines successful. These are things we're really, really proud of overall at Cray. And Seymour gives us a great quote that kind of frames a little bit of what I want to talk about today, which is that the future is seldom the same as the past. And so, like I said, while we make this huge commitment overall to some things that will remain at Cray, and you can always kind of count on Cray for, things have to change. Technology changes, and we have to move with that technology overall. I talked about one of the things that won't change is our commitment to innovation and this investment that we have in R&D. This kind of frames what I want to talk about overall. The areas that we really focus on, when we look at where we're investing our R&D over the last many years, dozen or so years, it's really in three big kind of buckets or three areas. One is around the system interconnect. Hardware, a ton of software architecture work that we do all the way through application work to improve the connectiveness of our systems overall. The second is software to get as much performance out of a system as possible and to manage that system very effectively. And the third area is really around what we like to call packaging technologies, power packaging and cooling, really about driving the overall total cost of ownership of our machines down over time, making them upgradable, power efficient, densely packaged, all those kind of things. We put it all together in this little pyramid that we call adaptive supercomputing, which just says we want to build this common system infrastructure. A lot of that is that system interconnect and packaging technologies. Put different processors into that infrastructure, kind of pick the right processor for the right application. And then above that, build a software stack that allows the user to take advantage of the complexity of these machines. And these systems are getting more and more complex all the time. And just in a few years, the complexity is going to go up another order of magnitude or so. So what has changed? It's been about 40 years since we shipped the first Cray 1 machine to Los Alamos National Laboratory in 1976. We shipped this, and really optimal design of supercomputers has always been around looking at kind of all levels of the system, processors, memory, storage, and interconnects. And I'm just going to talk a little bit about each of those areas today. But these shifts in these technologies over time has really had a big impact in how these systems are programmed, how we interact with them. Our users and workloads on these machines have changed dramatically over this same period of time. It used to just be physics using Fortran. That was pretty much what was running on Cray supercomputers. Today we have pretty much everything, humanities and the arts running on Cray supercomputers, big data running on Cray supercomputers. It's pretty exciting to see how broadly used these systems are becoming over time. So let's just jump in. I'm going to talk a little bit about processors. We'll start there first. Overall, I don't have to tell you guys, but processors have changed a ton over the last few years. If you go back to the Cray 1 and just look for kind of the first couple iterations of Intel kind of x86 processors, the attack of the killer micros time frame, you can just see the technology changes that have happened. When the Cray 1 was done, we were really constrained by logic. Like, how much logic do we have? What can we do within that overall? Just in a few years later, transistors everywhere, and you get to do a lot of different things with all these transistors. Now, as we look at things, it's really all about power. And when our architects look at our next generations of supercomputer, their main design constraint is really power, because we can't kind of regulate voltage as we scale up these chips anymore. And so performance per watt is not keeping up with Moore's Law. Moore's Law is doing pretty good, but we can't scale voltage like we used to be able to do. And so we can't really keep up with that over time. I think everybody's seen a version of this kind of a chart that says the transistor counts are still going like crazy, but clock speed, power, instruction level parallelism, all of that stuff is pretty much flattened out for us. And so lots of times our CTO, Steve Scotty, likes to say computers aren't getting really faster, they're getting wider. And we have to think about how do we take advantage of this and all the levels of parallelism that we now have to take advantage of in order to make these things very efficient. From an architectural perspective on processors, we've had to respond in different ways. One is start to move to multi-core. An Intel Xeon processor would be a great example of a multi-core processor overall. GPU computing, on Blue Waters, we have a version of both of these. We have the AMD processors, we have the NVIDIA GPUs. Much, much simpler processors, a huge number of them, looking at taking advantage of those. And then vector computing is coming just this year in a few months, or pretty much right now. We just shipped out, in fact, last week, our first set of cabinets with Xeon Phi processors in them. This is, again, a very simple processor using vector technology and to get the huge performance boost that you can get. So huge bunch of different processors. All of these you have to think about quite differently in how you want to target applications and where you want to program to. At Cray, around processors, our view anymore is we don't think we should build them. We used to build our own vector processors. We just don't think that that's the right place for us to be spending our R&D investment right now. Our view is look very closely at all the different processors out there, and I've listed a few here. There's a few more that we could throw on to this mix overall, but really kind of think about different options. Look at sustained price performance and programming models and what customers want. How do we physically enable these different chips into a supercomputing infrastructure, and work with each of these companies to help to improve those systems, improve those processors for high-performance computing, because many of these processors are not originally targeted at the high-performance computing market. You know, the bummer of our business is the whole server business is about $50 billion in revenue, and high-performance computing is about 10. And so we're not the biggest market for these guys, and especially more and more as the cloud infrastructure guys, you know, buy more and more of these processors, they're starting to get keyed up more and more for those kinds of workloads, which are very different workloads than the workloads that we're typically working with in high-performance computing. So we do a lot of work, collaborations with each of these companies in helping to figure out how to enable these processors for high-performance computing, and then build great systems around whatever ones that we decide to pick. Because we can't use them all. We got to make some choices, pick a few, and build some great systems around those. So from a CPU standpoint, we have all of these changes. Our response to that has been to work with these vendors, enable them for supercomputing, and then build these very high bandwidth infrastructures around these processors. Let's talk a little bit about memory. Memory has changed dramatically through the decades. You can kind of see here, we went from very, very small memories to then a nice shared memory region, and then we had to move to distributed memories, and now we have like hybrid memory systems on different nodes. So memory's changed quite a bit over the past few years. And we've done a lot of work in looking at the memory subsystem of different processors. This is actually some work that was done at our performance group inside of Cray. They've come up with something that we call a Cray mark. A Cray mark is basically a broad set of applications that we've decided really represent a broad workload on a machine. And we found very high, you can see these numbers along the bottoms. I've taken out the names to protect the innocent. They're different processors. And so these are, how do these workloads perform on these different processors? And you can see it's very highly correlated with the memory bandwidth of these processors. One thing that a lot of people, when we buy computers, we look at flops. It is not very well correlated with floating point operations. And this is going to get worse and worse over time. And so I think over time we like to talk about exascale, petaflop, and exaflop. It actually is almost meaningless as far as what's real performance is about anymore. The correlation between flops and real sustained performance is, as you can see on this chart, not very similar at all, not very highly correlated. And so one of the things that we have to really look at is not just the floating point operations, but how do we take advantage of the full processor and the full system overall. I think one of the biggest changes that we're going to see over the next few years, and if I could leave you with one thing today, it would be don't focus so much on the processors over the next few years, because the processors is not where the action is over the next few years. It's going to be in this memory storage hierarchy. This hierarchy has been pretty simple for us. We have a CPU. I'm going to ignore all the caches and stuff. We can make this chart more complex if we wanted to, but we basically got a DRAM. We go out to a hard disk drive, a bunch of them that we access in parallel, and then we move our data out to tape over time. One of the biggest changes that's going to happen over the next few years is a real big deepening of this hierarchy. We're going to have a near memory, like a high bandwidth memory between DRAM and the CPU. We're going to have a far memory like 3D XPoint or some non-volatile memory technologies that will be out between that DRAM and our first layer of storage. Our first layer of storage may be on the node, maybe off the node, but will likely be flash, and then we'll have our hard disk drives, and then we'll have our tape or object storage kind of out here. This is, I would say, a huge part of the work that's going on at Cray right now is to figure out how do we take advantage of this deepening memory hierarchy. It's going to hit us this year, by the way. Xeon Phi will be really, I think, the first. If you want to, you could kind of say GPUs have started us on that path with the GDDR, faster memory, but high bandwidth memory is really coming with Xeon Phi and will continue to roll out through basically all the processors over time. This is going to be a big, big change because this on-package memory allows us to get back that kind of really good bandwidth to floating point ratio that we've enjoyed in the years past and we haven't seen over the last few years. And it's pretty exciting, but it's smaller. And so we're thinking about how do we deal with this smaller amount of very high bandwidth memory. We think of all these memories as, well, we can use, this high bandwidth memory if we need performance, and we can use this, let's say, lower bandwidth but very high capacity non-volatile memories if we need the capacity. But these memories are very far from each other. This hierarchy is very, very deep. And so managing data in this environment is not so easy. And many of us have thought about, some of these memory technologies we may actually start to use as tiers of storage technologies, even though it's sitting on the node and you can access it like memory. And this is going to be a big part of how we think about programming these machines over time. But I will say this high bandwidth memory on package is one of the biggest things that we're excited about over the next few years. I mentioned we're going to get it this year. Xeon Phi, this will be kind of the first one. If you could see out here, I got to point this way, I know. I got out here on the Xeon Phi package, we have this MCD RAM, 16 gigabytes of memory, MCD RAM, very, very fast memory. We've done a bunch of performance work. I will tell you, if you can use this memory and stay in this memory, this chip is very, very fast. If you can't, it's a bit of a struggle. And we have to really work on how do we take advantage of that and what do we use. And it's a good perspective of how do we use compilers and tools and optimizers and stuff to take advantage of this amazingly fast on-package memory on a chip like this. Let's talk a little bit about storage. There's an interesting fact. So in the US, there's like 50,000 storage units. In the US. So if you added up all the McDonald's, all the Starbucks, all the Arby's, all the Taco Bells, you still don't get to as many storage units as we have. People like to store stuff. And what we found in high performance computing is you guys like to store stuff too. And so we got to kind of work through how do we deal with this. And this is a lot about this storage and memory hierarchy that I just talked about. But we've been pretty simple. I mean, from the very, very early days of storage devices like this, we've basically used rotating storage. And over time now, we just started striping it and using parallel file systems to get higher and higher bandwidth beyond kind of a single spindle. But as I mentioned, this hierarchy is changing dramatically. It's not just changing from the technology, it's also changing from a cost basis. And so now all of a sudden flash-based technology is becoming cheap enough to be potentially our primary storage system. And we like to think about disk is moving now to be kind of the new tape, and flash is going to be the new disk overall. And then there's going to be a bunch of technologies to kind of bridge that memory flash kind of layer that we're going to have, whether that be things like Intel's 3D XPoint or phase change memory or a lot of different resistive memories that are out there. And we're starting to get these different ways to kind of leverage kind of inexpensive, typically unreliable storage, but enabled to be very reliable through different object-based technologies, whether this is looking at technologies like Ceph or Amazon S3 or what we can do in the cloud and such, and bringing these things together. And then looking at different ways to kind of organize our data and access and interact with our data is becoming more and more important from a storage perspective overall. The first step, though, is to build in this next layer, right? So this flash layer. And we've done a lot of work at Cray. We just brought out a product that we just started with called data warp. It's basically just a flash layer. So between your Lustre or GPFS parallel file system and the memory, we've added in a new layer here. And a lot of people think of this thing as like a burst buffer, but I'll tell you, kind of a burst buffer is like a use case of this. There's many, many other ways to use it. Many people have used it as a local storage, so you can now start to think about this and use it just like you had a local disk on your node, because you know we don't put local disks on nodes because it's not so reliable and not very scalable, and you can't package it very densely. A shared model, one of the things that we've decided to do is allow it to be persistent. So if you have a workflow where you want data to go from application to application across a workflow, you can keep that data pinned persistently right in that very, very high bandwidth storage environment. And what we've seen is that the bandwidth of this is about 5 times what we can get with disk at about the same cost. We can't get the capacity yet. That's going to come over time, but we can get the bandwidth. And so how do we leverage this as a layer between the parallel file system and the supercomputer overall is something very exciting. And because it's right on the interconnect of the machines, very tightly integrated, that's going to become a really, really important technology over time. So we're just starting this. We just shipped this to a number of customers. We did a little work at NERSC on their new Cray system that they're kind of halfway through installing. The first piece of that was a bunch of Haswell nodes. We're going to upgrade that with Knights Landing nodes over time. But we did 12 million 4K reads and writes on the machine, 12 million IOPS. This is a number that is so far beyond what we can do going out to a parallel file system today. It gives us a machine that typically parallel file systems have been great for bandwidth, not good for IOPS. Now we can use small files and do a lot of small file work. This is another huge advantage for us to kind of take the pressure off that parallel file system in doing the things that it's not so good at and moving that up into this flash tier layer. So pretty exciting for us overall about just some early work that's gone on with these data warp nodes. As we look forward at Cray within storage, we explore more and more new areas to go. You know, extending this data warp concept to be the primary storage. Remember, flash is going to be the new disk. I feel like saying, you know, like green is the new black or something. Looking at these very low-cost storage devices and trying to figure out how we can leverage them within this hierarchy. One of the things of having a flash layer is right now the storage access software stacks are too heavyweight. So with going out to a parallel file system, you don't even notice it. It's kind of in the noise. Going out to flash, all of a sudden, you see that overhead of that stack. So we got to rethink kind of the software stack, especially the low-level stacks, and really trying to improve both the scalability and looking at different ways to organize data, taking a lot of what's gone on in the database and what's going on in the big data world and seeing if we can apply that in different ways to kind of access and manage our data. And then a huge part of it is just getting kind of enhanced telemetry and analytics off these devices. Storage devices are very, very hard. When we have problems in a parallel file system, it is very hard to diagnose. And so we have to get a lot better about getting telemetry data off these systems and being able to analyze that. And I'm going to talk about that a little bit more in a second. System interconnects is just another area that I want to talk a little bit about. We started building this chart as we started to move to multi-core processors. And just looking at the top 20 supercomputers in the world, how many cores were in it. And you can see we just had this exponential rise going on. We stopped building this chart in 2010. We were doing it, and it was obvious. We were like, this wasn't going to be, we knew where this was going, and it's continuing to go in this. But as we get more and more processing power out on each individual node, the system interconnect to keep that node fed with data becomes more and more important. Otherwise, we can't efficiently use all that power. And even today, we use a very small percentage of those flops that are available out on a node. And so the more you can get out of there, the better price performance you can get for your supercomputer, and the more performance you can get overall. Cray's had a long history in interconnects. Just as we moved to distributed memory machines, the first one being the T3E, we had a 3D torus interconnect that had very unique technologies, these E-register technologies that allowed us to move data in a shared kind of way across the machine. Then we moved on to C-Star, and we really focused on scalability and building out this interconnect to huge scales and building a connectionless protocol in order to get very, very good scaling on those machines. Gemini, which is on the Blue Water system, was another big step forward. So a new router design, much faster messaging that we could get on the nodes, and much higher resilience that we could get in the interconnect overall. And then recently, we just brought out our latest interconnect, Aries, which is actually a new step forward in architecture of the interconnect. So we moved from a torus to a dragonfly architecture, which allows us to move around the machine with much fewer hops and much faster, much lower latency as we transverse the machine, but also kind of very high global bandwidths. One of the issues with toruses is you couldn't get very high global bandwidths that you can get like in fat tree networks. And so we were able to get the bandwidth kind of characteristics of a fat tree and the latency characteristics of a torus overall. And starting to build more and more capability into the interconnect itself, like hardware collectives and adaptive routing and doing link level reliability on these machines, and starting to use optics now. As we start to move forward, these machines are getting bigger and bigger. We need to use optics to transverse these machines overall. If you just look, this is kind of a 2 cabinets of an XC40 with the backs taken off. A 2 cabinet group, which is about 768 sockets, not about, exactly. Where within a single chassis, there's actually 3 chassis in each cabinet, so 6 chassis in this diagram. We move data just across a backplane. Within this 2 chassis cabinet, we move it across copper cables, and then outside of these 2 chassis cabinets, we move it optically. Overall. So we use kind of different levels of technology at different levels of connectiveness for the machines. Over time, this is going to continue. So our next generation, we believe, will use copper just in a single cabinet and then have to do optics outside of that cabinet as the messaging rates get faster and faster overall. One of the things that we worked with a lot, and we actually partnered with NCSA on this, is looking at job placement. We found that job placement really, really matters on Blue Waters. And in a bunch of great work at NCSA and with Cray and a few of our partners, did some really great work to really look at how can we place jobs better on systems. But moving jobs around has some utilization impacts overall with your machine. It's a good trade-off right now with Blue Waters, but we would prefer you not having to make that trade-off. And so one of the things that we worked with Aries and this Dragonfly network is to kind of make it placement insensitive. We did a little bit of work that was published from Sandia, where we did kind of perfect placement of a set of jobs, and you can kind of see that on the far left there. Those are basically the seconds that these jobs ran in. And then we kind of randomly placed them in 64 node blocks, and then we randomly placed them across the whole machine in about the ugliest placement that you could ever get. And we only have a 3% variance from kind of the worst case placement to perfect placement on the machine. If we were looking at Blue Waters, I don't know what this number would be, but let's just say it would be a very large number, much larger than 3, probably a 0 or more on the end of that. So it's a really big step forward. And things that we learn, like I said, every time we build one of these machines, we want to learn so we can build the next machine even better. Another thing that we talked about is this connectionless protocol, which is one of the things that came in recently. This is a work done out of Sandia where they compared the Cielo machine that's at Los Alamos, which is the Aries interconnect, with a system that they have called Red Sky, which is a FDR InfiniBand based machine. And what you can see here is with nearest neighbors, they look kind of the same, But as you start to scale, then InfiniBand can keep on scaling, and we can keep on doing that. Same with kind of irregular communication patterns. We can get really this scalability. So this different protocols, all these different pieces of the network become very, very important at scale. And when you think about the kinds of scale of a blue water system, this becomes very, very pronounced in those types of machines. The last area I want to talk about is workloads. One of the things that we are really seeing, and I mentioned this a little bit earlier, is we are having a much broader user base and a growing user community that's using supercomputers today overall. And these guys don't come to us just with Fortran and MPI, but with a lot of different types of languages and a lot of different ways to program these machines. And our systems have to get better at using these other types of languages, which they're not so good at right now. And we've done a lot of work over the past few years to broaden this way that you can program these machines overall. Because, pretty much from our history, in 1976 when we shipped the first machine to Los Alamos, through not many years ago, it was pretty much all scientific models. It was a physics model, for instance, that somebody would put on the machine and really look at trying to model reality. And more over the past few years, people have started to want to do this same thing with data. And many experiments are turning into data experiments that we used to think about as scientific experiments. They're really just generating so much data that we want to do the same kind of modeling with data. And we actually want the output of these data models to feed into scientific models, and the output of scientific models to go into analytics models over time. And one of the biggest challenges for us is this huge wave of data. So if you just think about a physical experiment today, or all the data is coming off all these sensors or the internet or our Fitbits on our wrists, there's a lot of data going on out there that we have to somehow figure out how to stream into the machine, how to manage, and how to put into these models overall. And so a big thing at Cray has been helping to think about how do we compute in this environment going forward, how do we store and manage our data in this environment going forward, and how do we do analytics in this environment going forward. One of the things that we've been thinking about a lot is trying to take our various platforms and converge those on a system. We just actually made an announcement here just a couple weeks ago about a new system called Eureka GX. This is targeted at the analytics world, but what we basically did is we took an aspect of each of our systems and put that together into one machine. So we took the standard infrastructure from our clusters, 19-inch racks, very, very standard boards and stuff. We took our high-performance storage from our Synexion, our Lustre file system that we have. We have this open analytics framework on our XC platform where we can run Hadoop and Spark and all these different applications in a very open way. We took the Aries network, so our high-performance network, from our XC system and brought it into this environment. And our Cray Graph Engine, which is really a very high-end graph analytics platform that we used to have a special processor just to process this. We've actually been able to take that technology, put that into the hardware of our Interconnect, and now be able to run this graph analytics package right on top of our Interconnect and move data around like we used to have to build special processors for, and bring that all together into one system. This is the first time we've actually taken our high-end supercomputing Interconnect and put it basically in a cluster and built this framework around it. So we're really excited about this whole convergence between all of these technologies going forward. As we look forward into the future, we want to take those kind of environments and we want to put that right onto the supercomputer. So taking that whole analytics environment, for instance, and putting that right on top of Blue Waters and letting you take advantage of that, just like it was an application or a set of tools available for you on Blue Waters. We call this our Minerva project inside of Cray, because we feel it's important to combine high-performance computing and analytics into a single system over time, because we have a lot of workflows. This is an example of a protein folding workflow where we do simulation, analytics, simulation, analytics, simulation, analytics across this whole workflow, and bringing that all together and not having to move the data on and off the system is a huge advantage overall. Another good example is at Google, they did this work with Go, and they had built an AlphaGo project, which was basically HPC under the covers, very similar to what IBM did with Deep Blue with chess, where HPC is under the covers of this basically analytics machine. Overall, when we think about new workloads like machine learning is very much an HPC style application, and something that we can do very, very well on supercomputers. So how do we take advantage of these new frameworks on top of these supercomputing infrastructures? We did a little work with ICM, which is out of Poland, a university in Poland, where we were doing graph analytics. They were doing it on our cluster platform, the CS400, and CS400 is this green line that you can see here. And then we ran that same platform, so we did a bunch of work when we could take that software and run it on top of our Interconnect and be able to scale that up in a very high-end, high-performance way overall for us on our high-end platforms. And this is an example of what we can do. We also did some work with the University of Oregon and NERSC doing the exact same thing with Spark. You know, Spark today is very much a big data application that people think about running in relatively small scale today. But we saw that you can run it in 10,000 nodes when you have a scalable infrastructure underneath this. So building these scalable infrastructures underneath these standard applications, not forcing the users to change their application or programming model or do some weird stuff to use a supercomputer, but use the actual application that they can run on their desktop on a supercomputer, but take advantage of this bandwidth-rich infrastructure that we built, enables whole new uses and whole new applications on our machine overall. We thought a lot about this analytics model on our machine, and one of the things we thought about is, could we apply that to using the supercomputer and actually getting more out of the supercomputer itself? We call this operational analytics. So we have zillions of log data coming off this machine. It's all put in different spots depending on what kind of data it is overall. Can we use this analytics technology to start to look at this on the machine and build a better machine and be able to diagnose problems better? We started this. We have something that we call SSA, or System Snapshot Analyzer. It's part of our service offering that we provide for free that allows a customer to get some of this data and do preventative maintenance. So it starts to tell you, hey, your file system is filling up, or whatever. This node is starting to go bad for whatever reason. But we want to do even more of that and start to connect the supercomputers with an analytics appliance that allows us to really start to do proactive usage of the machine, not just from an operation standpoint, but also from an application standpoint, and looking at application data and helping people to figure out how do we do better job scheduling placement, how do we improve application performance, how do we build basically dashboards with all of this log data, so you don't have to stream through the log data, but it's done for us, and we get information out of it instead of just a bunch of data as you get in logs today. So we're really excited about this as being something that's moving forward inside of Cray, and will help us to help you guys to take advantage of these precious resources over time. One of the other things that we get asked a lot about, especially with new users, is about the cloud. And we talk a lot with people about the differences of a cloud and a Cray supercomputer and where they're the same. And there's a lot of similarities and a lot of differences. Our forecast is that the future is going to be partly cloudy. So the cloud has a lot of great advantages. Ease of use, it's elastic. You can leverage a huge bunch of software infrastructure that's out there for you. You can pay as you go. It's very quick to deploy. Overall, all really, really great things in systems. But we also found that it's pretty darn expensive if you use it a lot. So we've done a lot of studies at about 40% utilization of a system, which 40% utilization of Blue Waters, Bill Kramer would be fired, I'm sure, the next day. So we get much, much higher utilization, like 90% utilization on supercomputers. But at 40% utilization, it's actually cheaper to own it than it is to go out to Amazon, even on very low-cost ways to get onto Amazon. So it's not so cheap. Moving data onto the cloud is hard, but pretty cheap, like free. Moving data off the cloud, not so free overall, and tough to do. And it's not the architecture of the systems out on the cloud aren't really good for real capability style workloads. And so we've done a lot of work to think about how do we start to bridge this gap? How do we adopt some of the advantages of the cloud and bring that onto machines? How do we allow access to supercomputers very similar to how you access clouds? You know, some of the early technologies like Docker and Shifter, which is a project out of NERSC to basically do scalable Docker on systems, and OpenStack, these are technologies that you're going to see on supercomputers. In fact, today we support all of these on our supercomputers, and over time we're going to move, for instance, all of our system management over to OpenStack with some special things on top of that to get the scalability that we need in supercomputing technology. So these are really, really great technologies that allow us to make supercomputers look and feel a lot more like the cloud and allow people to access them very easily. So you can build something on your laptop, build a Docker container, and then ship that to a supercomputer and run that at huge scale very, very easily, not needing to have all the different capabilities that you need for that specific application, or have to change the application to make it work on the supercomputer overall, because we can ship all that together in a Docker container. OpenStack's really exciting for us. Our first OpenStack-based managed system is that Eureka GX system that I just talked about. That's completely managed through OpenStack with some Cray add-ons over time, and you'll see OpenStack move to our clusters and then to our high-end supercomputers over the next few years. All of this is really starting to come together for us. All these different technologies that I just talked about and what we call our Shasta system. This is just our next generation supercomputer. We're targeting it for 2019 timeframe overall. Because if you look at our systems today, our two big supercomputers, the CS400 or CS Storm, which is our GPU version of it, it has a bunch of advantage of being very standard, a standard, industry standard open software stack. You can put a variety of different interconnects, InfiniBand, Ethernet, OmniPath on it. It's very flexible. We can have a lot of different node types and stuff. And on the other hand, our XE40, very scalable, very, very optimized, a very tightly integrated software stack that allows us to get that scale and performance out of the machine overall, an interconnect and such. And so Shasta is going to basically allow us not to have to make those trade-offs of one versus another. We'll be able to pick what types of cabinets do we want. Do we want industry standard cabinets or optimized cabinets, or some of both? What kind of power and cooling do we want on the machine? Different processor, more flexibility in different processors and node types. A very tightly integrated stack or an open software stack, depending on what you want to run on that machine. And things like operational analytics and different interconnect support overall. So we're really excited about making this system and developing this and not forcing these kind of trade-offs that you have today in computing. We actually announced our first Shasta award. It's a system called Aurora that's going to go into Argonne National Laboratory, not so far from where Blue Waters is. A really great partnership with Intel in building this system of taking kind of next generation Intel technology and integrating that all into our Shasta infrastructure and building a software stack to take advantage of all of that. So this is something that's really exciting to us overall, and we get to target not only supercomputing workloads, but also these data analytics workloads over time. I just want to wrap up by talking a little bit about Exascale. So Exascale, we really believe, is kind of going to be the last era of CMOS. We think that CMOS has probably got 10 or so years, 10 plus years left to it, so there's still plenty of room in the world of CMOS. But kind of this next Exascale era will be the last kind of CMOS era over time. As we think about Exascale, we think about what kind of node structures, and we think about nodes that are probably going to start out in the 10 to 20 teraflop range, and over that era time move up to maybe 50 teraflops over time. This on-package memory that we talked about, and then this new generation of very deep memory storage hierarchy that we have to take advantage of. A system, as we talked about, getting wider and wider, but order 100,000 nodes, around 30 megawatts in the early stages of Exascale as we move forward. And interconnects that are very much a low diameter, so maybe being able to hop through the whole machine in 1 or 2 hops overall, which will get really, really great global bandwidths and latencies overall. But if you look at all these components, over the next kind of decade, they're not going to change so much. Supercomputers aren't going to change so much from our current model. We're going to have to think about how we use this memory storage hierarchy and such, but overall, the system structure, it's going to be more or less what we have today, with a lot of different technology thrown into that that we have to think about and take advantage of. After CMOS, I'm not even going to talk about. That's a whole nother talk overall. When is that going to happen? What are the leading technologies for? We're super excited to see a lot of new work in this area overall. We're, of course, following it very, very closely at Cray. But just to say that I think that to go back where we started, there are some things that are definitely going to change over the next few years, and there's a number of things that aren't going to change much. When we think about what is going to change, what the best processor is at whatever time frame over the next 10, 20 years is going to change a lot. And so what we want to build is a system that's basically insensitive to the processor, or can take advantage of whatever processor is the right processor for the job. Applications, workloads, algorithms, users, those are all going to change a lot. That's going to continue to evolve, and so we have to build systems that are more flexible to allow these changes overall. And this memory and storage hierarchy, as I talked about, is going to change dramatically, and probably the biggest change that's going to affect us as users of systems. And what won't change, as I mentioned earlier, at Cray, our commitment overall to innovation, our partnership with customers, and our commitment to stand with you guys. Because while a lot of things change over time, some great things never change. So with that, I will stop, and hopefully we can open it up for questions overall. Questions this morning? Yeah. So, oh. There we go.
When you put together this analytics machine, with all these pieces from your existing systems, and when you compare the lessons you learned from building that machine with, let's say, lessons learned from Blue Waters, what stands out?
I think what stands out most from building that machine is that we had to figure out, when we build a supercomputer, we kind of force people into a way to program that machine and a way to use that machine. With these analytics infrastructures, we can't force users to do anything. We have to use standard Hadoop or standard Spark or a standard NoSQL database. And so we had to figure out which technologies could we use that we could get leverage of with very open source commodity kind of software stacks on top of it. And so that really learning, we did a bunch of work with the AMP Lab in Berkeley to look, for instance, at Spark and these things. We did a bunch of work with Hortonworks and Cloudera in looking at Hadoop and how to take advantage. So how do you, because all of these software stacks were built without thinking about a supercomputer. They were all built for cheap commodity clusters using gigabit Ethernet. And so if you put a very high bandwidth, for instance, interconnect, it's not really going to take advantage of that. So how do we build some low-level software to automatically take advantage of those supercomputing capabilities? This is what I think about more and more as we expand our users of these machines, is we have to do things that take advantage of this kind of infrastructure without forcing them to change their applications. Otherwise, we just won't move those users over. So I would say that was our biggest learning overall. Yeah. Other questions? You got to wake up this morning. Come on, guys. I can repeat it if you want.
Thanks very much for the very interesting overview of where you're going. Being very up close and personal, Cray has been, in partnership with NVIDIA. As you move forward, and you talk about Aurora, that's very exciting. But a lot of questions to be addressed as you move forward to that big system.
Yeah.
Can you comment on, as you look into the future, having your experience with the GPU line, what do you see as the relative merits between the Aurora and the Summit line?
Oh, great question. So how do we see kind of the Aurora system, which is built off Xeon Phi, versus the Summit machines, which are built with NVIDIA GPUs? First of all, I just want to say our partnership with NVIDIA hasn't ended, right? In fact, it's bigger than it's ever been. A huge bunch of work that we're doing. We're actually working with them right now on building a machine learning kind of platform inside of leveraging supercomputing technology to build this machine learning platform. We really think the processors are not going to be so different on these machines. When you really look at how it's structured, there's pros and cons of different ones, how to take advantage of it and how to use it, and the difficulty or the ease of doing those things. But when you look at it just from a system architecture standpoint, not so much different. The memory and storage subsystem of these machines are getting very different, and the interconnect of those two machines are very, very different. And so when we think about supercomputers, we think about really moving data around the machine. And so we're obviously very partial to Aurora, but you could take the Aurora framework and put NVIDIA GPUs into that same framework, which we will definitely do at Cray, and build a very high bandwidth kind of infrastructure and same kind of machine overall. So I don't think about it so much as differences. I think about it as kind of trade-offs between those two architectures. And I quite honestly don't believe that there's one processor that's best for all workloads. And so having a mix of processors is a good thing. On Blue Waters, we spent a lot of time talking about what's the mixture of Intel's or AMD Opteron nodes and NVIDIA GPU nodes, and what should be the balance of those machines, where are the applications today, and as we all know, the applications have progressed over time. And so I think these kind of hybrid systems are going to be very normal. Blue Water is kind of out in front of that trend, I think, overall. So I think what you'll see more and more is systems that have both types of node infrastructures, but in a much higher bandwidth, kind of more of an Aurora-style bandwidth infrastructure overall. That's how I think about those two.
And how do you expect application programmers to deal with both types of processors in terms of their software stack?
Yeah, so the application side is the trickier side, right? Is how do we do this? So more and more, there's a lot of work going on to think about what is that kind of programming model of the future. MPI plus OpenMP is the likely candidate overall. We're kind of encouraging people to go that direction. We were early supporters of OpenACC, which we still support today for GPUs, but OpenACC won't be really a great platform if you want to make that code portable over to a Xeon Phi platform, for instance, or even an AMD GPU, if you think about that, right? Because we want to be open and make these codes portable over a long period of time. And so there's a lot of work to try to build a programming layer that will be consistent and portable across platforms. And then you can decide whether you want to do things that are going to improve performance on any individual platform, but then you start to sacrifice portability. So we'll see how users kind of think about those kind of two infrastructures over time.
What is the future of Cray's own parallel programming language on the new architecture?
Our programming language, like Chapel? So at Cray, we've developed a programming language called Chapel, which we're doing a bunch of work in. We're super excited about, and have had a number of people really kind of use this language, especially it's a very high-level language. Overall, we're very committed to it. We don't think Chapel's for everyone. Chapel's for people that want, a kind of more like it's for the same people that would think about using Java or Scala or something like that on a machine. If you're going to go down and use MPI and OpenMP and all those things, you don't need a language like Chapel. But what we're finding more and more is where Chapel's getting adopted at a few places is where they're bringing in new programmers that don't know anything about MPI and Fortran and things like that. And they can be much more productive, much quicker with languages like Chapel, higher level languages over time. Over time, we think they'll use lower level languages too. So we use Chapel, it's open source, we've open sourced it. You can use it on any platform. We use it as a way to kind of experiment and explore things. We've done some exploration in data analytics, using it for data analytics, using it with GPUs, et cetera. So all different things. We continue to remain very focused on building that out too, but only as one choice of many in the programming languages world.
So I have a question. So it's great to see the great diversity of processors, the different memory hierarchies that you talked about, and the performance. I completely agree about the memory bandwidth being the main driver for performance or real performance. But another factor is the costs of those things. And without having some idea about the relative cost of these different processors, different ways of doing stuff, you might be uniquely positioned to comment on the cost structure, because the other thing that we know is as investments are made, that has driven some of the performance factors that you were showing in your earlier slides. So can you talk at all about where you see, relatively speaking, we thought at one point processors were free. Now we know that they're not free. Memory used to be the thing that was going to be really expensive. Now it wasn't as expensive as we thought. Can you comment at all on where the costs of these future systems are going to be driven from?
Yeah, I think if you look at systems today, I would say the biggest change in cost over the last, let's say, 5 years has been in the interconnect. So the system interconnect as a percentage of the cost of a total system has gotten to be higher and higher. And that's because it's getting more and more important overall as the performance of these individual nodes gets higher and higher. And so we've seen the shift in cost being in that direction. As we look forward, a lot of the shift in cost is going to be onto that silicon package. And I say silicon package because on that silicon package is going to be a processor, memory, and potentially some interconnect technology all on that same package. And so as we're looking at systems that are out 5 and 10 years like we're looking at today, out through the exascale kind of time frame, that silicon package is going to be a huge percentage of the cost of the machine. But it's going to contain a bunch of different technologies on it. And so the trade-off is going to be which of those technologies, so if you look at that memory and storage hierarchy that I laid out, which ones of those technologies are going to be really important for you? Like Aurora, we're looking at building a machine with no DRAM. So Aurora may have, and we're going to do a bunch of studies on this before we make our final decision, but Aurora may just have on-package memory, as much as we can get, and then out to 3D cross-pointer, kind of non-volatile memory, so much slower memory, but very, very high capacity memory for those people that need very big memories. No DRAM potentially on a machine. Very interesting from that trade-off. And so we really think, Bill, that it's very difficult right now to know what those right trade-offs are, because all these technologies are just on paper pretty much. And I think we all have had enough experience in the industry to know that you got to do real studies on real stuff before you can make really good trade-offs of what these different technologies are. But I would say that you'll see a shift to kind of interconnects being a huge part, this on silicon, or this piece of silicon with high bandwidth memory being a huge component of the system, and the other components of the system shrinking in cost overall. And that's how it's going to play out. More and more, we're hoping with all the new processors potentially coming out that it puts more pressure on that processor pricing and getting that processor pricing down, but that on-package memory becomes very expensive too. So that all looks kind of as one big piece and one big component.
And when it's all on one package, then you don't have everything mixing with everything else, right? You start to get partnerships of certain things on.
Yeah, and we'll have to make, you'll have different choices of what's on package and what's off package over time. So it's going to be very interesting. Some interconnects will be right on package, only can attach to those processors and no other processors. And so it becomes really important to think about preserving choice in this environment too. That's another thing that we think about a lot.
Any other questions? In that case, then, thank you very much, Pete. We really appreciate you coming down.